Thank you. So we'll switch to the next presenter, next speaker. So I will welcome Tianji on the stage. So Tianji is from China, but works at the University of Nottingham since 2018, I think. And yes, that's it. So yes, and so the University of Nottingham is one of our academic partners. So Tianji will present you a very nice topic about advanced windings in electrical machine.
Thank you, Corentin. Okay, good afternoon, everyone. It's really a great pleasure to attend the JMAG user conference organized by PowerSys in the beautiful city of Leeds. And I mean, on behalf of University of Nottingham and PMC Group. Also, this is the first time for me to attend a conference with almost all experts from industry sector. And it's really interesting and helpful for me to have learned a lot from the state of art challenges and potential solutions, concepts to tackle the most up-to-date problems in industry. So today, from the academical side, I'm going to present some research work on hairpin windings, which was initiated from our group in 2019. I will present some simple case study to highlight our research findings. Okay. Somehow I cannot page. Oh, okay, this is the one below. Okay. Thank you. Okay, before presenting the details about hairpin windings, I will have a very brief introduction about our research group. So basically, our research group is called Power Electronics and Machine Center. We're based in University of Nottingham with more than 150 members, including academics, researchers, and PhD students. Our research activities mainly lie in three aspects. We do research and development of electric machines and drives, and also from manufacturing point of view, we're keeping investing in the advanced manufacturing capability to investigate the influence and also the benefit of advanced manufacturing in e-machines. Also, within our group, we have been improving our test and the validation capability in terms of either of both automotive application and the aerospace sector. So basically, our group received more than 70% of research funding from industry, and we're very close with our industry partners to develop high-speed, high-power electric machines to really trying to find the cutting-edge solutions for the next generation products. A very quick review of what we have done. Basically, before COVID, our research group mainly received funding from aerospace sector. So basically, we've developed quite a few prototypes. For example, this actuator machine for helicopter. Also, this blue one is basically an aircraft starter generator with 32,000 RPM. We also developed some direct drive high torque density machine for the electric taxing. And also we've been actively engaged in the EFANX project in Europe, and we've developed a 4 megawatt level high power generator for hybrid aircraft propulsion. As said, we mainly have been focused on aerospace sector, but after Brexit, we have received ever increased funding on automotive sector, and we have put more and more research effort into integrated automotive e-drive solutions. For example, we have cooperated with Cummins to develop heavy-duty 350 kilowatt level high power density IPM machine. And we've also cooperated with tier one supplier like GK Automotive to develop the high-speed, the next generation high-speed automotive powertrain. Okay. So basically, I will start the brief introduction on the hairpin winding configuration. I think most of the attendees today, you must be very familiar with hairpin winding already, because this is a really hot topic, especially in automotive industry. Basically, hairpin winding compared with random round winding, it basically features a much improved slot fill factor, so much reduced DC copper loss and higher efficiency. Also, the uniformity on the end winding arrangement with also a very careful winding layout design could completely eliminate the potential circulating current issue, which is really problematic for random winding high frequency operation. And also hairpin winding has also been widely recognized as a key technology solution to further boost the power density of traction motors, because this kind of winding configuration can really combine with very intensive cooling strategy to significantly increase the current density and current loading on the electric machine. So this plot shows basically a side view of our 350 kilowatt heavy duty traction motor development with multiple layer hairpin windings. Basically, on the insertion side, we will need to bend the rectangular shaped wires into a U shape and insert this kind of preformed windings into the stator slots. After that, on the bending side, we basically need to further widen the conductors and twist the conductors of each layer to make the terminals be ready for the welding operation, as well as the post welding installation process. So overall, at the end of today, we have already identified that clearly hairpin windings could feature high power density, high efficiency, and potentially reduce the NVH issue because of the higher rigidness of the stator configuration. We start by looking at the very fundamental aspect of hairpin winding, which is the winding layout configuration by using JMAG, of course. So basically, take this figure as an example. We for hairpin windings, there is always the configuration of the insertion side and the welding side. From the insertion side, we really would lead the pin shape number to be as reduced as possible, because it's directly related to manufacturing cost. And on the welding side, usually we would lead them to be completely uniform for the twisting operation. And basically, to achieve the winding configuration without any circulating current, there is also an important feature that we need to achieve, which is always called transposition, which means if a phase winding of hairpin has more than one branch, and then basically all the parallel branches, they need to contain the conductors from all layer of slots and all the phaser on all the phases belonging to one phase pole group. Okay, and we have identified that based on this kind of requirements, there are different kind of connections needed. For sure, we need uniform welding. Apart from that, from insertion side, there are many pin shapes which are regular. So basically, most pins they should be within the same shape, at least from within one layer. And also there are some jumpers, special connections we call jumpers needed for the purpose of transposition. Some jumpers, they need to achieve something we call phaser change. Some jumpers need to achieve the function of layer change. And also if the winding layout goes from the top layer to the bottom layer, which needs to go back, then there's some special connection we call single layer connection, which is also of course special as well from manufacturing point of view. So for academic level research within our group, what we really would like to seek for is, based on JMAG, what kind of winding layout would really be feasible from manufacturing point of view and also from electromagnetic performance point of view. Taking this 48 slot, 8 layer, 8 pole winding configuration as example, because 48 slots, 8 pole is very popular and that's being widely applied in automotive industry. So if we follow the most basic design rules of hairpin winding connection, there will be jumpers. However, from 2D section point of view, there will be jumpers crossing each other, which from manufacturing point of view will create challenges in the shaping of the pins. So in order to tackle this kind of challenge, we basically have a sort of solutions to shift the design layout to cancel all potential connections on the insertion side in terms of this kind of jumper intersection. This kind of jumper intersection, from one side, it increases the difficulty in manufacturing, but it's still achievable in some specific cases. Here I show some 2 pictures from existing industry products, where we can see that there are some special connections which actually achieve this kind of special jumper connection. But again, from manufacturing point of view, we will still need to reduce the number of this kind of special connection as much as possible for the simplification of manufacturing. Okay. Then we have identified that JMAG is really a nice tool for us to look at this at the very initial stage. For example, we can use the winding template in JMAG geometry editor, and we can very conveniently use this kind of winding layout template to define the shape and the connection of the hairpin winding layout. As we see on this, this end winding pin shape, they are very quickly generated by the JMAG designer. And we can further identify the special connections, such as this single layer connection, such as the terminals, as well as all special jumpers. And we can have a very intuitive view that whether it could be easily manufactured or not. Also, based on the 3D FEA, we can simulate whatever we model. So JMAG could also be used to quickly evaluate whether the layout design is reasonable in terms of eliminating all circulating current. And also, we can directly evaluate the end winding losses by building suitable and reasonable end winding models. Okay. We have also identified the flexibility in winding layout configuration, because basically hairpin winding follows the typical wave winding features, but it is inherently multiple layer. So compared with random winding, it definitely features increased flexibility, which significantly increased its options of winding layout. For example, if we would like to achieve short pitch connection, we can easily shift the fixed belt by one round or by multiple rounds without changing the coil pitch from full to short pitch. We can also further increase the asymmetry level in terms of short pitch by making the specifically arranging the insertion side and welding side. I think this kind of configuration with Q equals 2 features a very nice characteristic, which effectively reduce the AC losses, because there are 2/3 of the slots in which laboring conductors are from different phases. So the proximity effect could be effectively reduced in high frequency operation. And also, by listing all of the possible options, we can calculate the potential pin shapes needed for manufacturing, and from a cost-effective point of view, we can select the design with the least number of pin shapes for the cost reduction. Also, we can flexibly summarize the potential slot pole combinations and compare it against random lap windings. And it's very interesting to see that there are some specific slot pole and parallel lumbar combinations which specifically can be used for hairpin windings and not suitable for lap windings. Okay. Also, we have identified that to feature very high power density, especially in high-speed region, there might be other promising slot pole combinations which could be potentially better than the classical 58 slot 8 pole. And in order to achieve reduced AC loss in high frequency operation, we basically need a higher number of layers and also a higher number of stator slots to basically obtain reduced conductor size, because it's basically conductor size related. In order to achieve this, we have increased the stator slot number, but unfortunately, sometimes we cannot go for very high pole number due to the limitation on the inverter side. So we believe that winding layout solutions with increased number of slots per pole per phase might be beneficial from high-speed operation point of view. For example, if we design the machine to be with 54 slots and 6 pole, which, as many of you know, has already been applied by some product, might be beneficial from losses and efficiency point of view. But simply for hairpin winding configuration, if we increase the number of Q, we increase the number of slots per pole per phase, there will be significantly increased difficulty in winding configuration, because basically under one pole, there are increased number of slots to achieve transportation. So potentially, based on the traditional winding layout method, configuration method, there will be much increased pin shapes. This is really not beneficial from manufacturing point of view. So within our group, we have identified some promising winding layout solutions with reduced pin shapes to achieve the high number of Q and also high number of winding layer number. Okay. Then basically I will introduce some specific case studies in our group by using JMAG. Again, in terms of slot pole combination, we did a very simple but relatively comprehensive comparison between the 48 slots 8 pole and the 54 slots 6 pole configuration. I mean, again, since IPM machine development, it inherently features multi-physics design with many rotor geometry parameters. Some of them, they are closely related to electromagnetic performance, while some others, like the rib thickness, the position of these bridges, as well as the rib angle, which are highly related to the mechanical performance. So within JMAG, we can very conveniently combine the electromagnetic and the mechanical design with this software itself. So basically, following this specific design optimization with consideration of different slot pole combination, but similar level of material usage, we have identified 2 suitable designs for, based on the common performance requirements, which features more or less 160 kilowatts, 18,000 RPM, and peak torque of 270 Newton meter. Very typical requirements for a passenger car. Okay. And based on JMAG, it's also very interesting during the conductor size shifting process, as we have identified that if we select typical operation points, for example, peak torque at the knee point, and also the peak power operation at peak speed, if we would like to select the most suitable pin size, I mean conductor size, which can feature higher output torque and power, but reduce the winding loss, it's interesting to find that basically low speed design and high speed design, they always, the selection of pin size, they are always in conflict with each other. For example, in low speed operation, basically the most copper loss components, they are DC. So we would like to have potentially increased pin sizes in terms of both conductor height and conductor width to get more copper usage and reduce DC copper loss. Okay, but in high speed operation, when the frequency goes high, the AC loss quickly become dominant, which indicates the design trend to have relatively reduced the conductor height and width. So a comprehensive design would always require us to combine both low speed operation and high speed operation to get the most suitable conductor size option. So we did this for both the 48 slot 8 pole and 54 slot 6 pole. And by comparing the efficiency map, we have identified that, of course, increase the slot number and also winding layer number is really beneficial from efficiency increase point of view. Also, we have done a thermal analysis to see the machine temperature distribution under both the peak torque and the peak speed operation. And we also identified that to feature high speed, high power operation, and increase the slot number and also increased layer number would be really beneficial in terms of balancing the temperature distribution in both low speed and high speed operation. Okay. Another very interesting but quick case study is about winding material. So nowadays we have heard increased voice from our industry partners that basically they would like to try the option of aluminum winding for the cost-effective purpose, as well as for the purpose, I mean, of sustainability. So based on the proposed winding layout of 54 slots, 6 pole with 10 layer, we further compared a bit the machine performance by using aluminum winding or copper winding. we directly go for this very, very high winding layer number and also relatively high slot number as well, because this would be potentially a boundary where if we have identified the difference between copper winding and aluminum winding, if we further reduce the layer number or reduce the slot number, then the optimization results will always shift to the direction that aluminum winding would be more beneficial, because under this kind of boundary, with reduced slot number or reduced layer number, the conductor size always increase, and AC effect becomes more dominant, which makes aluminum more fancy, because aluminum features more or less 60% increased DC resistivity, which is of course not good from DC loss point of view, but is really good from AC loss reduction point of view. Okay. So again, before the optimization of the stator size, we have done quickly reasonability and rotor geometry design. We basically have identified designs which can feature high output torque and output power in both MTPA region and field awakening region, with a reasonable range of torque ripple. And we have also carefully selected the geometric parameters in this rotor, in this very typical double layer rotor, to make sure mechanically the mechanical stress is within its safety margin. So again, it's a preliminary multi-physics design stage. And again, at the second stage, we have looked into different conductor size options by using copper or aluminum, respectively. And we have identified that still, based on the 60% difference in the resistivity of the winding material, aluminum would still challenge the machine design, especially in its lead point in peak torque operation, because simply at this kind of point, DC loss would be quite challenging, and we will need to definitely have increased conductor size to reduce the DC loss components. And based on the same performance requirements, we have found that the optimum conductor size of aluminum is only slightly higher than the copper case, because again, we need to balance the output performance and losses behavior in both low speed and high speed region. Okay. Another interesting phenomenon we have identified, that even with this kind of increased stator slot number and many layer number, we have identified that in high frequency operation, for example, based on this specific case, with peak fundamental frequency of 1000 Hertz, we have compared the current density and loss density level along different winding layers. And it's interesting to find that by using copper, of course, this kind of total to DC loss ratio will quickly change when the conductor position change from the slot bottom to the slot slot opening. But the interesting thing, we have identified that even by using aluminum winding, the overall losses would generally still be higher, but the loss density, the peak value of loss density in the area where the conductor is close to the slot opening, in fact, copper winding features even higher loss density compared with aluminum. And this really gives us a hint that in our future developments, using a hybrid combination of copper and aluminum might be a promising solution if we target on high speed, high power operation. Okay. Then basically for the conclusion, from our group, our capability on advanced 1D technology mainly on two aspects. From on one side, we have researchers who are really focused on developing the state-of-the-art traction machines, either for passenger cars or heavy-duty off-road vehicles, and we can develop prototypes which features multiple layer, multiple slot number of hairpin winding prototypes. And on the other hand, our group has put quite a lot of investment into this kind of flexible hairpin winding production line. So basically, currently within our group, we can start with the bobbins of pin, and we have the facility to straighten the pins, straping the pins, and also do the preforming of the conductors. Afterwards, we can also customizedly fit the pins inside our stator slots. And on the welding side, we also have the laser welding and laser cutting machine for the other side of the conductor. And also we have flexible arrangement of post-welding installation like trickling and porting. So this basically features a whole flexible manufacturing chain of hairpin windings. And apart from hairpin windings, our group are also very active in the analysis of, research work on other high performance winding types, such as the lead wire, which we have used a lot in high-speed aerospace machines. And also we will have a customized continuous hairpin equipment as well. Basically, the hairpin, which features zero welding joints. Okay. Apart from this, we also have the flat wire, which sometimes we call it edgewise. We also have this kind of facilities to design preformed concentrated winding prototypes. Okay. Apart from the design and the manufacturing of prototypes, our group can also have the capability of high power, high speed test and validation. For example, we have a number of direct drive, high speed, high power traction rigs, which feature the torque from 200 to 500 Newton meter with the speed up to 20,000 RPM. We also have a specific environmental test cell, which features 500 kilowatts and 25,000 RPM. Within our group, we also do some more fundamental research, such as the magnetic materials characterization. This is also a very hot area because, as presented by previous colleagues, they are really power loss related. Okay. Okay, I think. Okay, as a summary, we have a academic team, quite a big academic team and researcher team. And all this presentation are based on two publications in which there are a lot of details if you are interested to dig in more. And also for further questions, we can either discuss here or please feel free to contact me by email. So, okay, thank you. Thank you for your attention.
Tianji, for your presentation. Do we have some questions? We can take maybe 2 minutes for questions.
Hello, thank you for the presentation. You said by increasing number of slots, you're going to reduce the AC factor of the machine, which is correct because you are reducing cross section. But at the same time, if you go to the extreme, you increase the slot stray flux, yeah, and hence increase AC losses. Did you find some break even, or is this still in development?
Yeah, thank you for the question. This is a very interesting question and important. So yes, there is definitely a certain limitation in terms of increasing the slot number. For example, with very typical outer diameter of 200 from 200 to 230, I mean, which features a very typical traction motor design. If we go to the slot number to be too high, for example, 96 slot. So basically, on one hand, this kind of selection would significantly increase the insulation, the part of the insulation which reduce the slot fail factor. And on the other hand, there will be significantly increased iron losses on the stator tools, especially in high-speed operation, because of the very high frequency slot harmonics. In terms of conductor loss, winding loss itself, based on our research work, we still find that if the conductor's size keeps decreasing, the loss density, based on the same frequency, will generally still decrease simply because of the reduced proximity effect.
Thank you.
No problem.
Last one. It's okay. Thank you again. Thank you very much. So it's time to have a break. And just to let you know that during the break, we will have another demo. So it will be done by Xavier from Hexagon. So Xavier will show Romax, SC Flow, Actron, which coupling with JMAG for your e-motor design. So if you're interested, it will happen in 10 minutes approximately. Okay, let's have a break.